problem 73 from chapter 12. It is our first example of a projectile motion problem. I will be showing you how to solve this problem using my method, but you are welcome to use the equations that are on page 41 in the textbook to solve projectile motion problems on your own. However, I think it will be worthwhile for you to learn this method that I'm going to show you now. And if you don't understand it completely, by the end of this problem, hopefully it will make more sense after we do a few more example problems. So for problem 73, we read that the water sprinkler positioned at the base of a hill releases a stream of water with a velocity of 15 feet per second as shown. So the initial angle is 60 degrees, so our initial velocity is 15 feet per second at 60 degrees. We want to determine the point B, where the water strikes the ground on the hill. Assume that the hill is defined by the equation y is equal to 0.05 x squared feet, and neglect the size of the sprinkler. Okay, so I have a diagram of what's going on here. In red, I'm showing the path of the water, and in blue, that is the equation for the hill. So I want to figure out where those two lines intersect at point B. Now, to start off, we're going to use equation 12.5, which actually is supposed to be a vector equation, and it's not written that way in equation 12.5. So let's rewrite this, and also let's bring the S naught over to the other side and just call this delta S. So that should be a vector. And V naught is a vector, so delta S is equal to V naught times T, but I'd like to call that delta T, plus 1/2. We have our constant acceleration, which I'm just going to call A, but we know that acceleration is downward and the magnitude is little g, times delta T squared. Okay, so delta S is the displacement. It points from the initial position to the final position. We already know what our vector V naught is. That's for the initial velocity. Delta T is the time interval between the initial and the final position. And the acceleration is pointing downward, we already said, and the magnitude is little g. So what I'm going to do now is I'm going to draw a diagram to illustrate this vector equation, and the diagram that I'm going to draw is specific for this problem. So in this problem we have the water starting here at the initial point and ending here at the final point, so the vector delta S would point like this. So there's my vector delta S. I'm going to take this vector and draw it down here. As long as it's pointing in the same direction as it was initially and the same length, it is the same vector. So there's my vector delta S, and this angle should be 60, whoops, not 60 degrees. That was for the velocity. Okay, so there's my vector delta S. Now I'm going to draw another vector for V naught. That's pointing at an angle of 60 degrees, but I'm going to take this vector, I'm going to multiply it by a scalar quantity, delta T. So this new vector is V naught times delta T, pointing at an angle of 60 degrees. So it's going to go like this. But before I finish drawing this vector, I need to know how long to make it. Well, if I add this vector, this is one vector, and this vector, it's another vector. So this is the acceleration being multiplied by a scalar quantity, delta T squared, and 1/2, which changes the length of the acceleration vector, but it's still pointing in the same direction. If I add these two vectors together, this gives me delta S. Remember that when I add vectors together graphically, I place them tip to tail, and then I draw the resultant vector starting where the first vector starts and ending where the second vector ends. And so, if I'm going to place these two vectors tip to tail and end up here, the acceleration vector I know is pointing straight downward. So my acceleration vector is going to be pointing down like this. So I'm just going to draw the velocity vector until I reach that vertical line. So now this is V naught times delta T. And if I add to that my second vector, which is 1/2 acceleration times delta t squared, then I get this resultant vector, delta s. So now I'm going to use that vector diagram to solve the problem. So right now it's a vector diagram, and I'm going to take this and I'm going to draw, well, I'm going to make two right triangles, which I can do by drawing a horizontal line here and a vertical line here. I have one right triangle where this is the hypotenuse, the vector delta s, and this is the base, and this is the height. I'm going to redraw it just so you can see things clearly. So we have delta s, which should still be at the same angle that this vector was and should have the same length. And then we have this distance here and this distance here. Now, going back to our original figure here, we had this vector delta s. We have the point B here. This is y, and this is x. You could call it delta y. You could call this distance delta y, and this distance delta x if you wanted to, but the water is starting at the origin, so we're just going to say delta x is equal to x and delta y is equal to y in this example problem. So the distance from here to here, so that's the distance, not a vector, is equal to y, this point here. But y is equal to 0.05x squared, and the distance from here to here is equal to x, and we have a relationship between those two sides of the triangle. Okay, and then I have another right triangle, which is like this, and I'm going to redraw that just so we can see it clearly. And this vector should still be pointing in the same direction and have the same length. This is V naught times delta t. This angle here is 60 degrees. These two right triangles that I had initially have the same base, so the distance from here to here is x. And then for this side of the triangle, if I go from here to here, this is y, and so this distance from here to here would be 1/2 times the acceleration times delta t squared. But I don't want to be working with vectors anymore. I'm going to use my right triangles to do some trigonometry, so I just want the length. So the magnitude, let's do this, the magnitude of the acceleration is just equal to g. Remember, the acceleration is pointing downward, but little g is always positive, so the magnitude of the acceleration is little g. And if you wanted to write the acceleration as a vector, you could say negative g j hat to show that it's pointing down. Okay, so this is 1/2 times g times delta t squared. Okay, now I'm going to use this right triangle and do a little bit of trigonometry. So I actually know the magnitude for the initial velocity, so that's 15, so I can put that in, but I'm going to save that for later. But this is the hypotenuse, and this angle is 60 degrees, so I'm just going to use cosines and sines here, and so I have V naught. Again, this is a vector, but if you just want the length, it would be the magnitude of V naught, which I don't think you really need me to write out, but anyways, there we go. So this hypotenuse has a length of V naught times delta t. If I do the hypotenuse times cosine of 60 degrees, that would give me the adjacent side, which is just equal to x. And if I do V naught delta t times sine of 60 degrees, that would give me this side of the triangle, which is equal to y plus 1/2 g times delta t squared. Now I want to put in some of the information that I have. So the magnitude of the initial velocity is 15. So let's say 15 times delta t times cosine of 60 degrees is equal to x. And then we can say 15 times cosine of 60 degrees is 7.5. So this is 7.5 times delta t is equal to x. Then we'll look at our second equation here. So V naught is equal to 15. I have delta t times sine of 60 degrees is equal to y, but y is equal to 0.05 times x squared. And I have an expression for x there, so I'm going to substitute that in just a minute. And we are working here with feet, and so we're going to say little g is equal to 32.2 feet per second squared. So we have 32.2 divided by 2, and then I have delta t squared. Okay, and then 15 times sine of 60 degrees is 12.99. So I have 12.99 times delta t on the left-hand side. Here I have 0.05 times x squared, so that's 7.5 times delta t squared. Both the 7.5 and the delta t are squared, since x is squared, plus 32.2 divided by 2, which is 16.1 times delta t squared. Okay, and then this is 0.05 times 7.5 squared, and that is 2.813, and then I add to that 16.1, so this is a delta t squared and this is a delta t squared, so I can add those together. So doing that all in one step, I have 16.1 plus 2.813 is 18.913 times delta t squared, and on the other side I have 12.99 times delta t, but I have a delta t on one side and a delta t squared on the other side, so I can cancel out a delta t on each side, and then finally I have delta t is equal to 12.99 divided by 18.913, which gives me 0.6869 seconds. I could round that to 3 significant figures if time was the only thing I was looking for. I could probably round it to at least 3 significant figures anyways. But because I'm going to be using this problem later on in the calculations, I just want to leave it with 4 significant figures for now to avoid any rounding errors. Some things to point out here. We got this equation here and this equation here by looking at the triangle, and because we are just looking at the lengths of the different sides, everything should be positive because it's the length. Whereas if you use the equations on page 41 of the textbook, they'd be related to what we have here, but the signs would be different. Okay, so here, when we look in the vertical direction, let's just say y naught is equal to 0. Okay, so we have the y component of the velocity times t, but that is what we had here. The y component of the velocity would be v naught times sine of 60 degrees times delta t. So if you're using the equation from the book, it would be negative, but it would also be it would be positive. It would be positive on this side of the equation. So we have it positive on this side of the equation. And then the 1/2 g times delta t squared would be on this side of the equation, which means then it would be negative. So this equation that we have here agrees with this equation from the book, which makes sense because we actually use that equation but in 2-dimensional vector form to draw the vector diagram. And similarly, you could compare this equation here to what they give you in the book for this equation when the acceleration in the x direction is equal to 0. And so we have the x component of the velocity, which is v naught times cosine of 60 degrees times delta t, is equal to x when x naught is equal to 0, as it is in our problem. Okay, so we used one vector equation, which is equivalent to this equation in the x direction and this equation in the y direction. That allowed us to find delta t. And what are we looking for? We are looking for the x and y coordinates when the water hits the hill. So we have to keep going here. But now that I know the time, I can actually just use the equation that I have here and plug the time in. So that would be 15 feet per second times 0.6869 seconds times cosine of 60 degrees, and that gives me x. So let's put x over there. That means x is equal to 5.51 feet. So that's what x is equal to when the water hits the hill. And now this is easy to find what y is equal to, because we can simply just go back to this equation here, and when x is equal to 5.51 feet, y is equal to 0.05 times 5.15 feet, and that gives me, squared, x squared. That gives me 1.33 feet. So we have our x coordinate and our y coordinate, and that concludes the problem. And because they only asked me to find the x and y position when the water hits the hill, that's all I need to do.